Hello, I'm Dr. Elizabeth Bell, and this is a mini lecture from my Chemistry 1412 class covering buffers. So today we will talk about buffers, which are an example of a specific type of aqueous equilibrium. Buffers are very important to biological systems. They help plants and animals achieve homeostasis. If you'll look in Chapter 16, Section 3 of your textbook, you'll see it says buffer solutions are very important in biological systems. Blood, for example, is a buffer solution that can reduce pH changes when acids and bases are produced in biological reactions. Cardiac arrest is one condition that can add acid to blood due to buildup of carbon dioxide that occurs when the heart stops circulating blood. In contrast, hyperventilation increases the amount of carbon dioxide removed from the body and can raise blood pH. The pH of human blood is carefully controlled in the pH range of 7.35 to 7.45 by conjugate acid-base pairs, primarily dihydrogen carbonate and its conjugate base, hydrogen carbonate. The oxygen carrying ability of hemoglobin in blood depends on control of the pH to within 0.1 pH unit. So a buffer is a solution which resists a change in pH when small amounts of strong acids or bases are added. A buffer is comprised of a weak acid and its conjugate base, or a weak base with its conjugate acid. Here's an example of a buffer made of acetic acid and its conjugate base acetate. A buffer can be made of any weak acid or base with its conjugate. Buffers are an acid conjugate base pair. And here is the same acetic acid acetate buffer from before. Let's add a small amount of hydrochloric acid to it. The hydronium ion produced from the HCl reacts completely with the acetate ion to form acetic acid. This reaction removes the strong acid by absorbing it with the weak conjugate base. This will result in the concentration of the acetate ion going down and the concentration of the acetic acid going up. Buffers can only absorb a small amount of strong acid or base. Once all of the conjugate base in this example is used up, the buffer no longer functions because it has exceeded its capacity. Now let's look at how buffer changes can be calculated. Here we have the same acetic acid acetate buffer reaction, only now we are adding 1 milliliter of hydrochloric acid to 1 liter of our buffer. The first thing that happens is the hydronium ion produced by the hydrochloric acid reacts completely with the acetate ion, creating more acetic acid. To keep track of how much acetate has been reacted and how much acetic acid has been formed, we must first convert the molarities to moles by multiplying the volume times molarity. The reason we do this is because when we're adding two solutions together, the volume may be changing so much that the molarities given are no longer accurate. The dilution equation must be used. Also, one cannot add and subtract molarities. The math just doesn't work. So, 1 millimole of hydronium reacts with 1 millimole of acetate to create 1 millimole of acetic acid. When you add that and subtract that in your Rice table, you will see that leaves us with 39 millimoles of acetate left over. And now we have 81 millimoles, of acetic acid. These values are our new initial concentrations in the Rice table of the buffer reaction aqueous equilibrium. Remember, a strong acid will react completely with a weak base. So we use these new values to calculate the pH. There are many different buffer systems which can be created and used. When choosing which reaction to use for a buffer, one thinks about what pH value they would like to maintain. For a buffer that needs to stay near a pH of 5, you choose an acid conjugate base whose pKa value is near 5. This would be the acetic acid acetate buffer that we have been studying today. If you want a buffer which keeps the pH near 2, use the hypochlorous acid hypochlorite buffer, which has a pKa of 2. This concludes our discussion of buffers. Please go to Sapling and do the associated homework assignments at this time. Remember, you can ask questions to get help. I encourage you to ask questions. Of the buffer after the hydrochloric acid was added. They are the same as the moles because the new volume is 1.001 liters. And dividing the moles we calculated in the previous slide by 1.001 liters does not change their value to within 2 sig figs. Some of the acetic acid breaks up into acetate and hydronium. We can neglect the X, which is added or subtracted to molarity, because the initial molarities are very much larger than the Ka value. Solving for X gives us the hydronium concentration, and then taking the negative log of X gives us the new pH of our buffer.